Okay, good morning. Zoom wouldn't let me in. I had to relog in. Share, there we go. There we go. All right. So today we'll talk about the object-oriented paradigm. It's just an introduction. We will talk at great length about this as we go through the semester. But the idea is to give you an overview of what to expect and to introduce some of the terminology that's used in Java. In earlier semesters, people were, hey, I'm reading the text and I don't get this code at all, so just introducing you to what code looks like. And then next week, we're going to start by showing you Java code and, of course, start out super simple and work our way up. But some of the ideas that we're talking about here. Here's our outcomes, as always, at the end of the week, which is today. Take a look at the outcomes, convince yourself that you've got them. A good way to do that is to explain them to somebody, like a roommate. Bother your roommate, tell them about all your classes, tell them what you're learning, and they'll hopefully ask you questions. And then if they ask you a question you don't know the answer to, that's an indication that either something's going to happen later in the semester to explain it, or you missed something. Okay, so the object-oriented software paradigm treats software as objects, and this may not make sense because software isn't real. So an object is something we can hold in our hand, right? We can touch it, bang it with a hammer. And you can't do that with software. You may want to bang your software with a hammer, but you can't. So let's start with real-world objects and then work our way into software objects. Real-world objects have a category or a name. Here's a picture of a stapler. Okay, what is it? It's a stapler. That's a whole category, right? That's a whole class of things. There's all kinds of different staplers out there. They do a similar job, but they are, oops. My computer's helping me again. No. There we go. I need to keep this going. There we go. Morning, Kevin. Okay. So the idea is that it's a category or a class of things that it falls into. It's a stapler. You can describe this particular stapler. You can describe its state, its color, the composition, made of metal, how big it is, where it is. Where's your stapler? It's in my upper left-hand drawer of my desk. Okay, so it has a state. How many staples are in it? That's part of its state. And then you can change its state. Right? You can staple something, which would reduce the number of staples that it has. You can try to staple something and it jam it. And now its state is jammed and your state is frustrated. So you can do something to, take the crooked staples out. You can reduce the number of staples, add the number of staples. Some of these attributes that describe the state are easily changed, some aren't. Like the color, probably not so easily changed. Red to blue. The material, probably hard to change. It's going to be metal no matter what. You can't turn it from steel to gold. So when you're thinking about your software objects, you start to think about, well, what attributes do I need to describe the state? In the context of the program that I'm developing, what do I care about this object? What are other entities going to ask about this object? So objects are things that have state and can change state. And they also belong to classes or categories of things. Another example is a chair. Chairs have such a wide array of specifics. Think of all the thousands of designs for chairs. But you can take a specific chair, and first of all, it's a chair. It's in a category. And we can break those categories down, right? We can have recliners and rocking chairs and office chairs, wingback chairs, right? So we can take that that class of chair and break it down into smaller classes. And then within those smaller classes, we can take a specific instance. So I'm sitting in a chair, I can describe its state. Its state is wood. It has a certain height and width and weight. It has a status like occupied or unoccupied. Right now, it's occupied. If I stand up, it's unoccupied. So we have a way to describe its state using attributes, and we have methods by which we can modify its state. You know, the stand up would be a method to change the state of my chair from occupied to unoccupied. A car, which is actually many objects, right? A car has state. Your car has state. It's probably parked somewhere. It has a location. It's probably turned off. It may be locked. Right? But you have methods by which you can change the state. You can lock or unlock your car. You can start or stop your car. You can change what gear it's in, reverse, drive, neutral, and so on. So this is the idea. Objects have attributes that describe their state, and then methods by which you can change the state. And we're going to take that basic idea and start to apply it to the software that you create. You take your software program, instead of a single program, like a top-down program, and instead you create a program that consists of a bunch of objects that interact with each other and work with each other. And for each object, you ask yourself, what attributes do I need to describe the state? What methods do I need to modify the state? And those are not trivial questions. It can become difficult. In this class, hopefully not too difficult, but as you move on and do different kinds of software, it can become tough. And particularly the methods tend to give more problems than the attributes. Usually we can describe what we need to describe the object or the class better or more easily than coming up with the methods. So here's an example where we can start to talk about software. Sheepdog game, which I'll use as an example a lot throughout this semester. In the sheepdog game, your job, you're a player and you're playing the role of the sheepdog, and you're going to move your sheepdog around, and the sheep always run away from the sheepdog, and you're going to try to herd the sheepdog into the pen. So, what objects do you think we can talk about here? What objects might you need for this game?
You're going to need the dog.
Yeah, the dog
sheep.
And the sheep object, right.
And
right.
You also need the pen and the walls around for
Right.
the entire encased area.
Right, so you need an environment. So we've identified three separate things. So there's three separate classes. We would have a class for the dog, and then we would have a class for the sheep, and then we would have at least one class for the environment. And again, this is a design choice, and it's not always an easy one. Maybe you have one class for the environment, and the environment contains that entire field of play plus the pen. Maybe you have a separate object or class just for the pen. Now notice I said we only had one class for the sheep, but there's 3 sheep in the game. How does that work? Well, once you design, the class is the design, then you have to make objects from that class. So we would have a dog class, which is the design for the dog, and then we would make one dog object in the game. And then we would have the sheep class, because all the sheep are the same, and we would create 3 sheep objects for the class, at least the way I drew this picture. And then we would have, say, a terrain class, and we would create 1 terrain object. So one of the benefits that we get out of object-oriented design right off the bat is once we do the class definition, we can make as many copies of that class that we want. So if I wanted to have a herd of 1,000 sheep, no problem. I still just have 1 sheep class. And then I just make 1,000 objects or copies of that class. This is very similar to, in the world, say, mechanical engineering, I might have a design for a bracket, And but that design for the bracket, that's not a bracket, right? It's a design for a bracket. It's on a sheet of paper or something, or in a computer model. And then I give that to a machinist and I say, make 1,000 of these, and they can just start pumping out brackets. So in the object-oriented world, you think in terms of objects. Now, by the way, a couple of notes. Think of graphics this simple, right? The Java all by itself, the way you're going to be using it does not have a super rich graphics capability. So, you're not going to build this beautiful 3D dungeon crawler game with glorious CGI monsters and things. There are other tools that exist in the world to do that. Tools like Blender and Unity and stuff like that. Right now, we're just using raw Java. They give you simple graphics. Think about the graphics being this simple if you're going to do a game-like application for your project. And then the other thing is, I'm not showing or not mentioning yet that we would need more classes than that. The dog and the sheep and the terrain are classes that we would need, and those describe the state of the game, but we have to show that game to the user. And so there would be a whole nother bunch of classes just to do the visual representation. And there is a clear distinction between what you see on the screen and what actually exists. I'm going to come back to that in a second, if I remember to come back to that in a second. So here's what your classes might look like. The sheep, what attributes do you need? And you have to think through, okay, what attributes do I need for the sheep? Let's see, I need to know where the sheep are. So I need an X location and a Y location. I need to know how fast the sheep are going in what direction. So you can either do a polar coordinates, speed and angle, or you can do it with a Cartesian coordinates, X speed, Y speed, current X speed, current Y speed. And the sheep can't increase speed forever. We don't want sheep going to the speed of light. So maximum speed. And then the same thing for the dog. We need to know where the dog is, X location, Y location. Where's the dog going? X speed, Y speed. How fast can the dog go? Max speed. And then we would want methods. And again, this is not necessarily an exhaustive list, but you might have move methods for the sheep, move methods for the dog. Maybe you have them vocalize. They have the ability to speed up and slow down. You have to decide what methods you want. And deciding on the methods can often be harder than deciding on the attributes. And as an example, once the sheep get in the pen, maybe I'll always make it where once the sheep get in the pen, they just stop moving. They just stop responding to the game. So I need to check to see if the sheep are in the pen. And that would be a good method to have, checking to see if the sheep are in the pen would be a good method. Now, where does that method go? Is that the terrain's job? Should the terrain check to see if a sheep is in the pen? Or is that the sheep's job? Should the sheep check themselves to see if they're in the pen? That method could go into either class. And I don't know that there's a best answer or a right answer. So you can find yourself, puzzling over, okay, I know that I need to have this method, but I'm not sure where it goes. And that's, quite frankly, is a problem that you can have well beyond this course. Making good class design. Now, as I have a note on the bottom, we also need methods or classes that will control the game and make the GUI and all that good stuff. And then, so let me go back to what I was going to say a minute ago. If this is what you see on the screen, this green field with the white sheep and the gray dog, be aware that that is a distinction, right? The sheep and the dog, that's the sheep and the dog. Notice there's no, the dog doesn't have anything about, oh, it's an oval or it's gray or anything like that. That's all about presentation. The sheep don't have any kind of graphical information in them. We can describe the sheep and the dog and the terrain fully without talking about how they're presented to the user or how the user views them. So here's the distinction. That gray thing you see as a dog is not a dog. It's a presentation or a view of the dog. The actual dog is code somewhere hidden behind, that the user doesn't think about. Same thing with those three white ovals. They are not sheeps. Those are sheep. Those are representations of sheep or view of sheep that we give to the user so the user know what's going on. But the actual sheep is that class with the objects that we created from that class, with the attribute values and the move and the methods. That's the actual sheep. The thing you see is the view. And I want to get this distinction early on in the course because it is quite frankly a difficult distinction to convince you of. This was a couple of years ago now, a student was trying to do a billiard ball game, a pool game. And, the billiard balls were represented as circles on the screen. And he was just having a horrible time trying to get them to behave correctly, right? To bounce off each other in proper physics formula. And the first issue he had when I started looking at the code, he was trying to make those circles have behaviors like cue balls or like billiard balls. And, that was my first comment is, oh, yeah, so there's a problem. That circle you see on the screen is not the ball. You have to have a software that models the board and models the pool table and models the balls and how they clang off each other. And then all that happens on the view is you update and show an animation that shows what the model is telling you. There's a distinction there. Even here, there's a distinction. You see that picture of me talking up in somewhere in your screen, hopefully. Are you looking at me? That's a real question. Are you looking at me?
Yes.
No.
And that's and yes is the common answer, and no is a more correct answer. You're not looking at me. You're looking at a view of me, a representation of me. I may not look anything like what you see on that screen. I might be a gray alien. I might be a disembodied AI. I might be 3 raccoons in a people suit. But what you see on the screen is a view of me. But that's not me. I'm here in my chair, and you're seeing a view of me, right? There's a distinction there. And getting you to, convincing you guys that that distinction is real in software can take a little bit of time. But once you get it, it's like, oh, I get it. I have to do all my model stuff. That's where I figure out all the formulas. And then all I do on the screen is echo whatever that model tells me to do. I present it on the screen. So for instance, here in the sheep-sheepdog game, if we have where the dog moves based on user input, and then the sheep move by running away from the dog, well, the sheep have to do a lot of angular calculations, right? Where's the dog? Oh, okay, it's at this angle away from me, and therefore I'm going to run away at a certain angle. All those calculations and attribute values are done in the model. And then what does the screen show? It shows a circle moving on the screen based on what the model told it to do. And again, we'll talk lots and lots about this as we go through. Okay, but back to the basic categorization of what objects do we need, what classes do we need. Notice I'm using 2 different words there, classes and objects. The class is the design. So you say, okay, I need a dog class, I need a sheep class, I need a terrain class, maybe I need a pen class. Okay, so then we design the dog, and then we make one. That's the dog class. We make one object of that class. We design the sheep class. Then we make 3 objects from that sheep class. There is a distinction between the class, which is the design, and the object, which is the actual instant. They call it an instance of the class, the actual thing you get to use in your software. And again, I'll bring this up again and again and again throughout the course. And in a few weeks, it'll become a little more clear. So if you're confused now, don't panic. This is an introduction, and then we go through these topics, 3, 4, 5 more times throughout the course. But I do bring it up early on because it's a common confusion that students have. So for example, someone who's building this class might create, this game might create a sheep class, but forget to build sheep objects. And then when they run the game, the thing crashes because they have no sheep. You have the sheep design, but no sheep, and you'll get something called a null pointer exception. It's very common. It's a very common error. The program crashes. It says null pointer exception. Student asks me, why did this program crash? And I'll say, well, you forgot. You built a class, but you forgot to make an object of the class. So you built your sheep design, but you forgot to build the sheep. Back to the bracket example. If I have a drawing of a bracket, I can't hang a shelf with that, right? I need an actual bracket. The design is the design, the class, and then the bracket object is an instance or an example of that class. So we might say, this is what we want to be, sheep and dog, you know, they have location, X speed, Y speed, max speed, and they all have the same methods, move, vocalize, speed up, speed down. Maybe, you know, you can, these are design decisions. And then we say those are the classes, the design. And then in order to make the game work, we would have, you know, objects created from those classes, 3 sheep objects, 1 dog object. What if I wanted to, you know, one of the benefits here is if I want to change the game and say, okay, I want it to be where there's 20 sheep, that's easy. Instead of making 3 sheep, I make 20 sheep out of that same class. I don't have to do a whole lot of coding. I just change a couple lines of code that says, okay, instead of make 3, make 20. Now let's look closer at the sheep and the dog. Notice they have the same attributes, and the names for the methods are the same. That was done purposely. The names for the methods are the same, but they behave differently. I want the dog to behave by user control, right? The person playing the game is playing the role of the dog, and they've got a joystick input or arrow keys or ASWD or something that allows them to control the dog. And then what do the sheep do? How should they move? Well, they should probably just run away from the dog. You know, maybe when the dog is so far away, they don't do anything. And when the dog gets closer, then they run away from the dog. And that's how the dog herds sheep, right? They know, the dog knows the sheep are going to run away from it. So they have the same attributes. They have the same kinds of methods. We certainly can give them the same names, but the behavior of the methods is different. And what we can do is take advantage of that. In the object-oriented world, you're allowed to take your classes and group them and categorize them in very general ways, and then do what we call extending those generic classes to more specific things. So for example, I might create this generic animal class, and notice it has all the attributes, it has the same attributes and the same methods as the sheep and the dog. And then I'll say dog extends animal. Literally, that's what you say. Dog extends animal. And what happens is you get all that stuff for free. So the animal attributes you get, that dog automatically has. And those methods in the animal class, that dog automatically has. And then you can overwrite or modify the method. So I can change the move method for the dog so it's responding to user input. I can change the move method for the sheep, sheep extends animal. I can change the move method for the sheep to run away from the dog. This is a huge advantage in object-oriented design. A huge advantage. It's, there's 2 really successful things about object-oriented design, and this is one of them. Okay, so the idea here is it saves you, number one, it saves you coding time. It helps with code correctness, because let's say I wanted to design the sheep and the dog separately, and I did the dog on Monday, and then I did the sheep on Tuesday, and on Monday I called the movement method move, and then on Tuesday when I did the sheep, I'm like, oh, the sheep always run away from the dog, so I'm not going to call it the move method, I'm going to call it the runaway method. Well, that's a needless complication. And we'll see later on in the course, not only is a needless complication, it actually prohibits you from using some design techniques that really simplify your code. So as a human, if you go ahead, Kala.
So the class designs the object, but the object is not the same as the representation.
Yes. So yeah, we've got 3 things going on. We've got a class, which is a design, and then you can create an object of that class. So I've got, in this case, I've got a sheep class, and then I can create 3 sheep. But then I also need to represent those 3 sheep to the user on the screen. So there's going to be a whole nother class that just draws the circles or draws those white ovals on the screen. Sound complicated?
Thank you. Yeah, I got it.
Yeah, you may be thinking, oh, this is a needless complication, but hopefully by the end of the semester, you'll see there's actually some elegance in this way of thinking. And what the elegance does is it separates the purpose of each of those things, so that when you're dealing with them, you can really laser in and deal with one narrow thing at a time. One of the problems, I'll talk about other paradigms and problems more a little bit later, but one of the problems of early code design is when you change something over here, then something over here got affected and nobody knew why. But by keeping things boxed into these classes, I can change the sheep class. And if I do it correctly, I know that nothing else in the program will be affected. Which is, great when you're modifying code, when you're maintaining code, when you're updating code. So this notion of extension. Now we're going to use the term inheritance, and I'm going to use inheritance and extension interchangeably. I know these are a lot of new terms. And again, if you're feeling confused, no worries. We're going to go through this step by step. I just want to give the overview of where we're going in this first lecture. So the reason it's called inheritance is because the dog extends the animal. All of those attributes that the animal had, the dog inherits those for free. So I don't have to say anything more about, X location, Y location, X speed, Y speed, max speed in the dog class, because it already got them from the animal class. It inherited them from the animal class. And the same with the methods. If the dog extends animal, it automatically has a move, vocalize, speed up, and slow down method. And then what I need to do is make those things unique to the dog. So for instance, I would change the move method so it responds to user input. I would change the vocalize method so it barks or howls or whatever I want the dog to do. I may or may not change, speed up and slow down. And then the same thing with the sheep. The sheep gets X location, Y location, X speed, Y speed, max speed automatically. It inherits it from the animal class, and then it gets move, vocalize, speed up, slow down automatically, and inherits it from the animal class. And then I would modify the move method to run away from the dog. I would modify the vocalize to, bleat. I would maybe modify speed up and slow down based on how close the dog is to me or something like that. You're going to use inheritance in your project. It's a requirement. And notice where the inheritance gained value. It's when the attributes were the same, but the behavior was different. That's the critical thing. The behavior was different, so the methods changed. That's really where you're going to be using inheritance. And again, we'll talk about this and talk about this. Okay. This is a core part of the object-oriented paradigm. It's really one of the great successes and useful features of object-oriented paradigm. We use inheritance, again, extension, inheritance. We talk about parent class and child class. And we borrow it literally from inheriting in biology. Oh, he's got his father's eyes. Well, how do you get this father's eyes? Inheritance. So the generic class is the parent, the specific class is the child. Now, how did this come about? This came about actually, the first true object-oriented language came from people that were doing a simulation of ships. And they recognized a couple things. One was that the ships were in categories or classes. And then they might have multiple objects of each of those classes. And they also recognized that a lot of those classes had a lot of things in common. So no matter what ship you have, you probably have things like tonnage, draft in the water, length, heading, speed, turning radius, radii. Right, those were all common. So they said, oh, we should create a generic ship class And then we can extend it to the individual kinds of ships that we are going to deal with. And those extensions are based on changes in ship behavior. So start out simple. Okay, I have a container ship versus a tanker. Oh, there's some slightly different behavior there in terms of how you load and offload cargo. Oh, then I can have a cruise ship. Completely different cargo, right? Human beings. Oh, and then we can have other kinds of ships. You know, we don't want our ships to sink. Ships should not go underwater. That's a bad thing. Wait, submarines, that's their job. Completely different behavior. Ships should not run into each other. That's a bad thing. Tugboats, that's their job. So you can put in different behaviors for the different classes of ships. So you have a generic ship, and then you can extend to the different ones that do different jobs, different behaviors. It makes it a lot less work for the programmer. The other thing that makes less work is once I design, say, a container ship, I can spit out copies of that container ship and have 30, 40, 50 of them if I want to. Virtually no effort on the programmer's part. So it offloads work from the programmer. It also guarantees code correctness. So if I said, you know, I'm working in a team of people and I need 5 tugboats and we need to do it from scratch. So I give, you know, 5 different people the job of giving me a tugboat design. I'm going to get 5 different tugboat designs, and there's no way that simulation will work. No way. So instead, what do? I give one person the job of giving me a tugboat design, and then I can make 5 of them. And they're all the same. I know they work in the simulation. If one of them works, they all work. So it offloads design. It helps code correctness. It helps code robustness. This notion of inheritance, you know, this notion of having a class by which you create objects and inheritance. It also, because things are consistent, it helps with code understanding. It helps with code maintenance, which we don't ever get to talk about much in academia. Code maintenance is a big deal in industry. How long does a software project last? Oh, you might take 2 or 3 years to build that product. How long does it last? 10 years, 20 years. And all that time, people have to maintain it. You know, minor updates, changing them to fit different operating systems, things like that. So it helps with a lot of issues that we have in software engineering. Now, it's not a magic bullet, right? We still have problems. When do you know you're going to use inheritance? When you have a class of objects that have a lot of things that are the same, but then you have different behaviors. One of the common projects people do in this class is, you know, the zombie chase game. You know, the player is running away from zombies. Well, you should have a generic character class. Extend it once for the player, extend it once for the zombies. Some people do zombie infection game, right? So they have normal healthy people and zombie people, and then they, you know, the zombies try to infect all the healthy people and take over, and the healthy people try to kill all the zombies. Same trick. You should have a generic class, healthy people class, zombie class. So this notion of inheritance is critical. So what have we gotten so far? Objects are software pieces where we think about the job we want them to do. We think about what attributes we need to describe them, what methods they need to change those attributes. And then we can start to think about, can we clump them together? Right? Sheep and dog got clumped together into animal, and then we extended to sheep and extended to dog. You may have, you know, some games, you know, dungeon crawler game, people might have a generic object class, and then that gets extended once for, say, defensive weapons, which gets extended again to shield and, I don't know, armor. And then offensive weapons, which gets extended to sword, battle axe, whatever. You guys are so violent, you know. And then you might have another object gets extended to potions, That gets extended to healing potions and, damaging potions. It helps you categorize your software. Okay, there's a lot of stuff there. So questions before we move on. Okay, you'll think of it. And again, we're going to go through this a lot as we go through the semester too. So if it's making sense to you, that's great. And if it's not making sense to you, that's great too, because you're gonna have access to this information again. It's not if I could teach you the whole class in one lecture, this wouldn't be a class. Okay, so why objects? Why did the object-oriented paradigm come around? There's basically three really popular paradigms of software programming right now. The first is, call it imperative or procedural. By the way, you can go on Wikipedia and find a lot more, right? Basically imperative procedural, which are basically top-down kinds of things. When you were in CS225 or EGR115, you probably thought along that way. I'm going to write a program to do this. And where do I start? I start at the first line of code and ding, 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 ding. And now in C, what's the first line of code? It looks for the main method or the main function. Okay, but that's where we start. We go down, top to bottom. Your code, generally speaking, can be thought of as one big hunk of code. The second one is object-oriented, where you, instead of having one piece of software for your code, you have a collection of objects, and these objects interact with each other. And then the third form is functional, which is much more akin to mathematics, and rather than having code that goes top down or objects that interact with each other, you have a bunch of functions, and then you create software through function composition. And when you take, those of you that will take CS332, you'll get exposure to the functional paradigm in that class. There are others out there. There are non-procedural paradigms and logic-based paradigms and tuple space paradigms and odd things like that. But those are the big three. And again, in EGR115 and CS223, you basically were exposed to the first one, the imperative, and now this is the object-oriented. Object-oriented is currently the most popular form of programming in terms of new software. There's a lot of legacy code out there, but in terms of new software, well, why is that? Well, there were problems in the old way. A functional, by the way, has never taken off in industry, so it's not that big of a field. But the imperative forms were huge all the way, from the 50s, 60s, 70s, 80s. Huge. But they had problems. Big problems. The code was getting bigger and bigger. More and more people were working on the code. Nobody understood the code. Nobody had a complete holistic view of what the code did. You would find weird comments in code like, don't touch this line of code. We don't know what it does. But when we remove it, the code breaks. So there were problems. And there was another problem. One of the reasons the code wouldn't work right, and wouldn't work right some of the time, which by the way is the hardest kind of error to catch, is because everybody had access to the same memory space. So here I am, I'm writing my code and I'm going to put this, data over here in memory, and then later on I'm going to go get it. And in the meantime, unbeknownst to me, somebody else's piece of code wrote something else in that memory space. So now I put x equals 10 in there, and then when I go get the value of x back out, it's all of a sudden negative 32, and I don't know why. So this notion of stepping on each other's data was a huge problem. You've heard of spaghetti code too, right? Code that I changed something over here, and for some reason, 1,000 lines away in the code, it's wrong, and I don't know why. Very hard to track, very hard to figure out. So this notion of data encapsulation was one thing. By containing or encapsulating the data in these attributes, you're controlling your own data. Nobody can touch it unless you say so. That's huge. This is the #1 big reason for object-oriented programming. 10 years from now, you don't remember anything about this course, but someone says, what'd you learn in that course? And you can say, I learned that data encapsulation protects the data, and that's the #1 reason for, the biggest success for object-oriented paradigm. Someone calls you at 3 a.m. What's the best thing about object-oriented? Oh, data encapsulation. You're in your interview. Why do you like object-oriented? Data encapsulation. I like to protect my data. Nobody changes it without my permission. So that's the biggest thing. Hugely successful. Of the big promises of the object-oriented world, this was a success. The next big promise was code reuse. The holy grail was, oh, we don't need to code anymore because all we're going to do is create all these objects. And then once we have all these objects created, people are going to say, oh, I'm going to write my own code now. I'll take this object, this object, this object, and I'm going to stitch them together, and now I have program. And that's a real thing. People do something, it's a community called component-based software development. People are trying to do that. So again, it's a different paradigm. This was not really that successful. That never really happened. It's been tried with object-oriented. It's been tried with component-based. The modeling and simulation community tries to do it with model objects. That's never really taken off that big. However, here's where code reuse has been a huge success in object-oriented world through the notion of inheritance. I don't have to write from scratch everything. I can take an object and extend it, and I already have all that functionality of the original object. You're really going to appreciate this when we get to graphics, because you don't have to do, if you had to build all your graphics from scratch, like pixel by pixel, you'd go miserable, more miserable than you're already going to be with graphics. But instead, you get to use all these pre-built classes that Java gives for you for free for graphic stuff. Same with all kinds of data structures. You get it for free. You just say, oh, hey, Java, I need to make one of these now. So code reuse has been very successful. Same thing with the generic ships and the individual ships, or the generic characters and the zombies and the player character, that kind of thing. Very successful. And then the third big promise was software understanding. Oh, now that we have objects, we're going to be able to understand how the software works, because it's kind of like if I build a machine and the machine is built up of different objects, I know how the objects relate to each other in machine, and I know how the machine works. So I can do the same with software objects. I'm going to be able to understand the software, because before it was all spaghetti code. It was all, right, it was a mess. Nobody knew anything about what the software was doing. And so now with object-oriented, oh, we're all going to understand. And it turns out that's not true at all. We still don't understand the software in complex software environments. It's still difficult. It's an intrinsically difficult software engineering problem to understand software. Different things have been tried in the past. Block-based programming and even programming languages were built, like Ada, that tried to coerce how things were built to improve software understanding. All of them failed. And object-oriented is still, code is just confusing. It's an inherent problem. Now, we will introduce techniques for you to try to reduce the confusion, but code is confusion. Code is confusing. Okay. Off of object-oriented into just basics and Java notation. By the way, this is normally 2 lectures, and I squished it into 1 because of Martin Luther King Day. So there is a lot here. I get that. Take your time, review it. Look at other stuff. Okay. Conventions. Now, when I say conventions, I mean these are just style guides. It's not a rule of Java. I will make sure you know when there's a rule of Java. And by the way, you'll know too, because you try to compile your code and it won't compile. You'll get an error message. As opposed to a convention, which is, this is how you should program. We strongly encourage you to program this way. You start your class names with a capital letter. Notice I did capital A animal, capital S sheep, capital D dog. That start class names with a capital letter. Then for your attributes, think variables here, attributes, you start with a lowercase and then you use X location. So notice I did X location with a capital L, max speed with a capital S, right? So it's considered good practice to have relatively long attribute names, that describe what the attribute is. No more of this X, Y, R, S, X for X location, Y for Y location, R for radius. Nope, nope, nope. Spell it out. X location, Y location, radius. Instead of T, it's thickness. If you have multiple thicknesses, thickness of outer core, thickness of inner core, long names. It took me a long time to get used to that, but I've become a big fan. Your code should be self-explanatory. If you're writing comments in your code to explain your code, what you're telling yourself is you're writing lousy code. So try to minimize the comments and then write good code. And part of writing good code is using names that say what the things are. The same for method names. Tell me what the method does. And I'll give you examples of how I believe that should be done as the semester goes on. If you have constant values, you use all caps. That's right away, that's a big flag. This is a constant value. So I might have like a max speed or something. If I wanted that to be fixed where people couldn't change it, I would all caps. That alone doesn't make it unchangeable, but that is a reminder to me. Oh, that's supposed to be a constant. Let's go back to data encapsulation. Everything that you create, every attribute, every class, every method, you have to declare it. You have to tell the compiler about it. And you get to label it private, public, or protected. Now, protected we hardly ever use. Basically, we're going to deal with private and public in this class. And by labeling something as private, what you're doing is saying nobody can see it. So if I have a private attribute, only entities inside that class can see it, change it, manipulate it. As a rule, make all of your attributes private. Protect them. Then you can have methods to modify them that are public if you want external entities to be able to change that attribute. And this is a common thing. We'll get into that. But make your methods private. Now, why would you do that? Because if you make the method by which those attributes can be changed, you get to make the rules. Nobody can monkey around with your attributes and give them stupid values. You can't put an aircraft at minus 10,000 feet. If I make the method that checks for that and doesn't allow that. We can't have sheep going at the speed of light. So this is a normal way to view to build things. Private attributes, public methods. Curly brackets are always blocks of programs. That's nice. We'll get into that when we look at like if, then, else, and loops and things. Parentheses are always used for methods. So whenever you see a parentheses, you know you're dealing with a method. Square brackets are used for arrays. Whenever you see a square bracket, you know you're dealing with an array. One thing that, I've only got a minute here. One thing that's going to be different for you folks that came from EGR 115, as opposed to y'all that came from CS225. In CS225, you learned before you can use a variable, in our case, an attribute or a variable, before you can use it, you have to tell the computer that you're going to use it. And you tell it by doing something called declaring it. Well, when you declare it, you have to tell the computer not only this is the variable name, but you have to say, here's the type of data it is. This is how I want you to interpret it. This one's an integer. This one's a string. This one's a character. So primitive data types that you're going to see: int for integer, double for non-numeric integer, non-integer numeric, char for character, and string for sequences of characters. Those are the common things you're going to see. So instead of just saying X location, it's actually going to be private double X location. Down there are the examples: private int X speed. Or maybe I want the X speed to be double instead of int. Maybe I want non-integer values. Then I could say private double X speed. Now, public double X speed is bad. Why is that bad? I made it public. I shouldn't let anyone mess with my data. The same thing has to apply to methods, but you have to talk about the return type. So if a method returns an integer value, it's public int, whatever the method is. If a method doesn't return anything, we need a word for that too, void. That's what void means. So you're going to see void in the code, and that's what it means. It's a method that doesn't return anything. Okay, Monday we're going to get into code examples. We'll start with hello world. We'll go through this again, and then we'll go through it again and again and again as the semester goes on. And within a couple of weeks, this is all going to be like, oh, how did I ever not know that? It'll be fine. Okay, I'm not gonna, yeah, really quick question. We're a little over, and some of you guys got to go to other classes. If not, have a wonderful day. Have a wonderful weekend. Thanks for being here. I appreciate it.